This is section 2.4, limits and continuity. In this section, we will try to get the definition, mathematical definition of continuity. Let's check what we have. Before we start, let's recall that we had the situation that finding a limit of the function as x approaches a often can be found by just calculating the value of the function at a. But this situation only applies if the function is a continuous function at a. Of course, a is in the domain. Yes, a belongs to the domain. And we will try to define what really means that function is continuous at a. And in general, continuous process takes place when things are happening without any interruption. And we have some physical phenomena that are continuous. For instance, displacement or velocity of a vehicle varies continuously with time, or person's height varies continuously with time. And for all current, like the current in a simple circuit varies continuously with the voltage applies to. However, we may have some discontinuity in the current, like the electric current. Yeah? But in general, we know what continuous, like continuous process. For instance, for the graph of the function, we may say that function is continuous graphically when we can draw a function without lifting the pen. Yeah? That means let's look at this. Let's look at, let's look at this. We have a blue curve, f of x, and this function is continuous. Yeah? Because when we can see function is defined at a, that means we have value exists. Exists, but f of a exists. A is definitely in the domain. And then if we will try to find the behavior, the limit as x approaches a, we can see the blue curve is approaching that dot, and that dot is at the level where the value is. We know the difference, correct, based on the limit definition. We know the difference between the value itself and the, let's say, blue, the answer of the limit. But yeah, they are the same, f of a, f of a. And then we can say, yes, this function is continuous function, has at that point a, yes, has no break, no like jumps, no asymptotes, no other like interruption. And that's what I mentioned, without like removing a pen from the paper, the continuous function can be drawn. Okay, that means this is the definition. Yeah? We have to have these conditions, like this hypothesis conditions has to be happened. f of x is defined on an open interval containing a, x equals to a, that means a is in the domain. Then f of a exists, is defined, and the limit exists. And then the function f is continuous at a, at a number a, if limit is the same like the value. Limit as x approaches a, f of x equals to f of a. And this is quite important to understand this continuity for the later like applications in calculus. Yeah, like maybe we will define some derivatives, integrals. We really need to know if the function is continuous function. Okay, because if we have this continuity, then we have a little bit of, different problem. Okay, let's see. That means I have example one, I have a function, the ping function, and a couple of interruptions. And looking at this graph, we have to figure out at which numbers of x this function is discontinuous and why. Okay, that's what we will justify. And so we may definitely notice that x equals to 1, we have a problem, correct? We can see we have a problem here. X equals to 1. We do have a problem here. Okay, x equals to 3. And we have a problem at 5. And 7. It's supposed to be 6, but let's keep it 7. X equals to 7. Okay, some of the values, that's all of them, 1, 3, 5, and 7. Some of the values are in the domain, some of them are not, but we will take number by number and we will investigate. But the first step, yes, please make sure that you will be also able to identify these numbers. Okay, x equals to 1. Okay, x equals to 1, the same graph. And now, in order to check what is happening and thinking about the definition of continuity, we have to check the value of the function at x equals to 1, and we have to find the limit as x approaches 1. Okay, but now we may notice 1 doesn't have, 1 is not in the domain. Yeah, that means 1 is definitely not in the domain. I can say x equals to 1, let me do this way, is not in the domain because we have no value. X equals to 1 is not in the domain. That means what I have. Okay, we have to find a limit, and usually we will focus on the left and the right hand side to make sure that the limit exists. But since 1 is not in the domain, function doesn't have a value. We remember we can draw a vertical line, and if the line intersects the curve, but actually it's not intersecting at 1, then we have no value. Okay, now limit. Limit on the left-hand side is 1. Limit on the right-hand side at 1 is also 1. Excellent. That means this is the justification. Limit exists is 1, but it's different than the value. Actually, value doesn't exist. That means we have one situation. And this situation, we may see just 1 point is missing. 1 point is removed. That means if the limit exists, and is different than value, or value does not exist at all, we may say that we have problem with 1 point. 1 point is removed. We will call this type removable discontinuity. Okay, removable discontinuity. Important, okay? Let's look at the next x value. X equals to 3. Now we are here. Let's do the same. Limit from the left, limit from the right, and the value. Now, on the left-hand side, yes, we can see on the left-hand side, function is approaching that solid dot. That's when we actually have the value, but we will wait here. It's approaching level -1. Yes. On the right-hand side, as x approaches 3 from the right-hand side, function is approaching 4. Yes, we can see this 4 on the left. And even indicate 4 and -1 on the right 4, on the left -1. And the value, when I will draw a vertical line, is intersecting here. That means value is -1. Okay, I can actually remove this because maybe. Okay, now what is the situation? The limit, because we have one-sided limits, different. Okay, then we know based on the definition, the limit does not exist. And the value actually is different. The limit does not exist, but the value is -1. But this is another type of discontinuity, and I can maybe hold my breath for like a couple of seconds, and you can answer aloud, okay, by watching this. Because you probably know, I am assuming that, or you may guess, function does totally different things. You see, like it's approaching here on the left, here on the right. That's what we will call, yeah? And how you don't even have to see the graph. Oh, actually, we get the information from the graph. Sometimes we can get from the formula. If these limits, left and the right, are different, we will be called that this is jump discontinuity. Okay, jump discontinuity. Because it's jumping, the curve is jumping. We can see from level -1 to the level 4, from height -1 to the height 4. Okay, that means we have removable and then we have jump. Now x equals to 5. Limit from the left, limit from the right, and the value. Okay, on the left-hand side and on the right-hand side, function is approaching the same dot. This dot is at the level 1, 1, 1. If I draw a vertical line, it's intersecting 5. That's mean value at 5 is 5. Okay, good. Good. Okay, now conclusions. Limit exists because one-sided limits are different, exist, but value is different. And value also exists, but is different. Okay? That means this is the same type. You probably may say that this is, I don't want to say, actually, it is jump, but it's not jump. Because we can see function, the main curve on the left and on the right-hand side is not jumping. It's actually approaching the same. Yeah? We can see based on the limit. We may still say that this is just 1 point removed, and it's placed somewhere else. At x equals to 1, the point was removed and was completely removed. But we can see function also. It's just removable discontinuity. Removable discontinuity. Okay? And the last x value that we have a problem, x equals to 7. Yeah, this is 7. Limit from the left, limit from the right, and the value. Value, we may notice, does not exist. Okay, and we may even look that this is a vertical asymptote. Okay, limit from the left and right is positive infinity because function is approaching that vertical line. And then value does not exist. We do not have a solid dot at the vertical line 7. Okay, and now limit is infinity, but we also know this limit is non-existence limit, and value does not exist. That means this type of discontinuity, maybe it's the easiest one to identify, because as soon as one-sided limit is infinity, positive or negative, we will call infinite limit. Infinite limit, of course, but infinite discontinuity. Okay? That means when the vertical asymptote is placed, we will say it's infinite discontinuity. Okay, that's when we have 3 types: removable, jump, and infinite. Okay, that's mean, please make sure, based on the limits or based on the graph, you can identify. Okay. And now I have this question. Let's maybe try. I don't know, maybe it's, let's see, let's do a couple of examples. Where are the following function discontinuous? That's we have a rational function, x squared minus x minus 2 over quantity x minus 2. This function is defined everywhere, but not at 2. Yeah, makes sense because we cannot have 0. And as x is 2, the value is 1. That's we will have just 1 dot. And what we can do, we normally supposed to find a limit. Yes, limit as x approaches 2 of the function We do not have the value. I mean, we have the value because value at 2, that's different part. The value at 2 is 1. And we can see we have definitely discontinuity because this expression is not defined at 2. That means we have to do this, and we will learn a little bit more in the next section. But at the moment, we may just use the algebra and try to simplify. Maybe we can avoid that x minus 2. Yeah? Because when we substitute 2, when we use the direct substitution, we're not even allowed because we will have 4 minus 2. We will actually get 0 over 0. Interesting, 0 over 0. But we will talk about this about next section, 2.5, right? The indeterminate forms. But when I do negative 2 and I think plus 1, we can see algebraically I can simplify this function. That means this function simplifies to that linear function x plus 1. And the line x plus 1 is defined at 2. And we learned that when the function is defined at 2, we can just substitute 2 plus 1 is 3. This limit is 3. And let me just check. Okay, I have the graph, but let me draw it. We have the function x plus 1. That means y-intercept is 1, x-intercept is negative 1. That means this function x plus 1, x plus 1, but this actually came from simplifying this expression. We still have to remember that this graph is not defined at 2. Okay, let me maybe to put a little bit more. No value at 2. value at 2 is actually 1. That means I will put the dot here. And now that open dot is at the level 3. But we can see it because this is just the limit, how function behaves, what function approach is approaching that open dot at the level 3. Okay? That means that you can see what I did. I use algebra to simplify and then use the direct substitution because this function theoretically is continuous function, but we use the previous information. Okay, that means this function has discontinuity at 2. Yeah, we can see because at 2 is definitely some interruption, and yeah, and it's just 1 point is the problem of 1 point. We will say it's removable discontinuity. Okay, let's, oh yeah, I did this. And actually I can say, okay, now let's look at also at this definition, just in case. We may also have something like one-sided continuity. We can say that the function is continuous from the right-hand side or from the left if function satisfies these limits. Limit as x approaches a from the right-hand side of the f of x is exactly the same like the value. And that means I can maybe draw a function like this at a, and I want the right-hand side limit, let's say 1 and 2. And we can see the right-hand side limit is 2 and the value is 2. That means we can say function is continuous from the right-hand side. Now this one, I can draw similar function at a, xy, we always have to label 1, 2, but I have to say this way. Limit from the left is 1 and the value at a is 1. Function is continuous from the left-hand side. Okay, that means that's also looks definitely this. We definitely have jump discontinuity, but we're just looking on one-sided. Okay, one side. Okay, I think that's, yeah. We just have like, yes, it's continuous at the endpoints. Okay. Now we also have the continuity on the entire like interval. Function f is continuous on the entire interval if it is continuous at every number in that interval. Also, we have a property of continuity when we will take two continuous functions, f and g at a, and some constant c. Then we will produce continuous function if we add or subtract or constant multiple, if we multiply them, divide them, or even make the composition of two functions. Okay? Of course, for the division, g at a must be not 0. That's and even if we do the inverse, yeah? If f is continuous on the interval with the range and the inverse also exists, you know, then that's another condition, then the inverse of this function will also be continuous function. That we can see we may produce this continuity by doing this algebraic operation, okay? Also, this theorem is quite important, yeah, and it's quite nice to understand this. Let's see. Any polynomials are continuous everywhere because the polynomials are defined actually everywhere. Domain of the polynomial function are all real numbers, and polynomials are the easiest function. Yeah, like I can it's just like nice and smooth function. Okay, but we can say that they are actually wherever they are defined, we have continuity. And now that means this is not a problem. Yeah, we may have a little bit of problem at first, maybe reading the next sentence, the next example. Any rational function is continuous wherever it's defined. Okay, that is on the domain, on its domain. And one of the example, rational function, the easiest rational function is 1 over x. When I will draw 1 over x, hyperbola in the first and the third quadrant. Yes, we may say right away, this function is not defined at 0 and has some discontinuity. And we will even say, we can even say infinite discontinuity. But the thing is, this is telling us, this theorem is telling us that the rational functions are continuous on the domain, wherever is defined. That means we completely ignoring that zero. And we will look, okay, on the left-hand side, yes, it's nice and continuous curve. On the right-hand side, it's nice and continuous curve. Yeah, that's how we can think. Rational functions are always continuous wherever they are defined. And the same root function, trigonometric functions. Yeah, we have no problem with sine or cosine, but for instance, tangent, tan of x, tangent is not defined at pi over 2, and then 3 pi over 2. Yeah, that's tangent, and every pi. But we're not looking at these numbers, we're just looking between. Yeah, we're just looking between, and it's nice and smooth curve. Okay, that's also an exponential function logarithmic. The same will apply. All of these functions mentioned on that slide are continuous on their domains, okay, wherever they are defined. And for instance, I can ask you a question like this. Find the largest set of points for which the following function is continuous. And you may see rational function, which actually is the ratio of the root function and some polynomial. That means rational functions are defined wherever they are. I mean, they are continuous wherever they are defined. We just have to find the domain. Yeah. For the algebra question, I will just ask you, please find the domain. But I can also ask you this continuous function on the domain. Okay, that's we have square root of x is always positive, and actually could be 0 because it's on the top, if the inside quantity is positive. That means this is one part. And at the same time, we have to respect the denominator is never 0. X squared is never 9. X is never plus or minus 3. When we combine this, not negative 3, not positive 3, and actually 0. X greater than or equal to 0 is this part, but we have to remove 3. Okay, that means domain is between 0 and 3, union from 3 to positive infinity. That means this is the set of x, the intervals where the function is defined. And this will be also intervals for continuity, because wherever is defined, we will have a nice and continuous curve between. We're not involving negative 3, actually it's completely outside, but we're not involving even 3. Okay, that's it. Please remember, always find the domain for the intervals of continuity of the rational function. Okay. And now another nice question. For what values of the constant c is the function f continuous everywhere from negative to positive infinity? And we have piecewise defined function. We have a linear function cx plus 117 for x's less or equals to 6. Okay, this is definitely continuous function. And for greater than 6, we have quadratic function. Cx squared minus 3. That's we have like, I don't know exactly, but we have like a line, yes, line, and then we will have parabola. And we want them to have the same. That means this will be continuous function. And I don't know what will be that point, but we have to find out for what values of c. That means what we really actually need. We need the limit on the left and limit on the right to be the same. We want them to meet the line and parabola. Okay, that means let's set up. We want continuous. That means we need limit of the function as x approaches 6. I took the 6 from here because 6 is the problem. It's the breaking point. From the left must be the same like the limit of the function as x approaches 6 from the right. And 6 from the left-hand side also will give us the value. I can also say it has to be the same like the value, but the limit on the left-hand side will be the same like the value. Okay, that means limit as x approaches 6 from the left-hand side. The function on the left-hand side is this one, equals to the limit as x approaches 6 from the right-hand side, cx squared minus. And since these lines and parabola are defined at 6, I can just substitute 6c plus 17. 6 squared will be 36c minus 3. And let's solve it for c. Subtracting 36 will be negative 30c, and subtracting 117, 120, negative. Dividing by negative 30, c is 4. Okay, that means when c is 4, the limits are equal. Okay, that we have to find the value c. Okay, and then we can draw it. I didn't, yes, draw, but then one function will be 4x, yes, 4x plus 17, and the next one will be 6. Oh, no, 4x squared. I don't have to square. 4x squared minus 3. But this one is for less than 6, less or equal this one. And then when we will draw these functions, this line, they will meet. Okay, we can even draw really quickly. And then parabola, this is 6. But what is that one, where they meet? Yes, we can substitute 6. Okay, that will be 24 plus 17. 141. 141. Yeah, that will be that limit if we want to do this. I think I added correctly. And also will be this 4 times 36 minus 3. It also has to be 141. Let me write a little bit nicer. 141. This is why this is 6. Okay. And I have one more example and we will be done. Okay. Similar. Yeah, similar thing. For what values of b? Okay, just the value of b. This function is continuous everywhere. Again, quadratic function, third degree polynomial, constant, they are continuous everywhere. But the problem is 1. That means we also want that parabola. I can maybe draw, I don't know how this parabola, at 1. I want this parabola and exactly at 1, the value is b, and this is the third degree. I don't know. We want them to meet. That means this parabola must have the value b for the limit, but we still have to find a, and this one. Starting the question, I can say the left-hand side and the right-hand side limit, they have to be the same. And then we will figure out the limit, and the limit is the same like value b. Okay, let's check. That's what we have to write. Limit of the function as x approaches 1 from the left must be the same like the limit of the function as x approaches 1 from the right-hand side. And the same like the value, but the value is b. Okay, let's focus on the first two limits. That means limit as x approaches 1 from the left. 1 from the left is less than 1. That means we will use this function. X squared plus ax equals to limit as x approaches 1 from the right-hand side, greater than 1 is on the right-hand side. We will do 2x cubed minus 2ax plus 5. Okay, that's quadratic function. Parabola is defined at 1. I can substitute 1. The same here. Third degree polynomial at 1, I can substitute 1. And actually, this equation has one only unknown. It's a. Let's compute a. It will be 3a, 7, 6, correct? A is 2. But this is a. Yeah, this is not b. We still have to figure out. But we know that this is also equal to the value, and this value is b, because we can see from that value at 1 is b. That's what we need to know. We know the value a. We really have to know what is that limit. Yes, this is the left-hand side limit. It's which actually is this also, yes? It's 1 plus a, and we know a is 2. That means this limit is 3. Let's look at this one also. This limit is right-hand side limit. It's actually defined like this. Actually, I don't like that line because I wanted to box, but I don't want to. Okay, oh, I want that nice blue. That means, let's see, 2 minus 2a plus 5. It's supposed to be 3 also. 2 minus 2 times 2, because a is 2. 2 minus 4 plus 5. 7 minus 4, it is 3. Okay, that means this is 3. Then B must be 3. Okay, a little bit of twist at the end, but the right-hand side limit is 3. Left-hand side limit is 3. The value must be also 3, and the value is B. Then B must be 3. Okay, but definitely the definition, the important part is this definition. Limit on the left, limit on the right-hand side must be the same like the value. Then function has continuity. And we have 3 types of discontinuity: removable, jump, and infinite. Okay, please check the first example for these types. Okay, thank you. Enjoy continuity and discontinuity. Thank you.